In this session, we will introduce internal measures for clustering validation. Remember, we just discussed several kinds of external measures. The lucky thing for external measure is we do have ground truths. We have expert knowledge, we have priors. Unfortunately, in many cases, we do not have ground truths. That's the reason we have to rely on internal measures. The internal measures based on the concept of clustering. That means we want the points within the same cluster. That means intra-cluster. They are very compact. They are close to each other. And we want the points in different clusters. That means inter-cluster distance. We want them as far apart as possible. That means we want them to be far separated. That's the reason we want to maximizing the intra-cluster compactness and also maximizing the inter-cluster separation. We want a trade-off between these things. So let's look at how we define this. Suppose we give a clustering C with K clusters, C sub 1 to C sub K. For each cluster C sub I, it contains n sub I number of points. Then we introduce the function W of SR, which is the sum of the weights on all the edges with one vertex in S, the other in R. For example, you get 2 points. You say this point is in this cluster, the other point is in the other cluster. You want to look at their weight. The weight usually can be defined like a Euclidean distance or whatever you are using for clustering. Then, based on this, we can say the sum of all the intra-cluster weights over all clusters should be defined this way. The reason is you can see this is C sub I, this is C sub I. That means both vertices are in the same cluster, so that's why it's intra-cluster. But one point A and the other point B, you actually use it to calculate twice because A to B, B to A, you actually calculate twice. That's why you have to divide this by 2. Okay, for all the clusters sum up together is I from 1 to the K's clusters. Then we define the sum of all the inter-cluster weights should be calculated this way, which is very obvious because one point, one vertex is in the cluster C sub I, and the other one is not in the C sub I, simply say in the other clusters. That's why it's intra-cluster. But since the 2 points you calculated twice, that's why you have to divide by 2. Then we sum up all these, essentially is I from 1 to K, all the clusters, we get a W out. Okay, that's the inter-cluster weights, sum them together. Okay. Now we also can see the number of distinct intra-cluster edges, because for I's cluster, you have an n sub I number of points. Their intra-cluster link, you have n points, choose 2. That's why you get this formula. Then you get all the clusters 1 to K, you sum up, that's why you get n sub in. Then for the interclass n sub out is calculated by one point is in cluster I, the other point is cluster J. They never are in the same cluster, so you want to calculate all the edges among different clusters. So that's the number of distinct intercluster edges. Then for beta CV measure is defined as W in divided by N in. You can think this is the mean intra-cluster distance. And you get W out divided by number of out. You can think this is the mean intercluster distance. So the beta CV essentially the ratio of mean intra-cluster distance versus the mean intercluster distance. Of course, for this measure, the smaller the better clustering, because the smaller means this is pretty small, it's quite compact, and this is bigger, it means it's more separated. That's a beta CV measure defined. Then we look at some other definition. One popular used one called normalized cut. Normalized cut is defined as follows. The normalized cut, this ratio, is defined by sum up of all the k clusters. For every cluster, you calculate in this way, or more explicitly, we can interpret in this way. This is weights of the intercluster. This is the weights, the sum up of the intra and intercluster weights. Okay. And for this ratio, you actually sum up from I from 1 to k, you get this normalized cut ratio. Of course, based on this, you want the intercluster to be far separated comparing to the intra one. That's why the bigger normalized cut value, the better the clustering. Then there's another definition called modularity. This is especially popular for graph clustering. It is defined in this way. You perceive this part is the same as normalized cut formula, okay, like this. But this part is a square of this. Okay. So that simply says this one is the observed fraction of the weights within clusters. This is the expected one. So modularity actually measures the difference between the observed one and expected one. So the smaller the value, the better the clustering, because the intra-cluster distance are lower than the expected one. Okay. So this is the modularity definition used for graph clustering.